All right, welcome everyone. There's a lot of people here. That's nice to see. First of all, thank you all for coming. This is our first seminar of the fall series. My name is Adeliza Flores. I teach chemistry here. And I joined the seminar series planning team about 5 or 6 years ago. And this is our 8th year of the seminar series, which means that there have been 28 seminars of this type in those last 8 years. So just a brief history of how this came about. So about 8 years ago, then biology faculty, now our dean, Nano, over there. A lot of you know her. She was the brains for conceiving the seminar series, and what came about was she had spent a sabbatical term at the lab, had the opportunity to go to a lot of good seminars over there. Unfortunately, they were only open to employees of the lab, so she collaborated with people from the lab to bring over wonderful speakers like Dr. Mukerjee today, right? So this is our 29th seminar, okay? All right, so before we start, just briefly to acknowledge the people who have been instrumental in putting these seminars together. We have, of course, the speakers to thank for coming over to share their work, right, that they're doing at the lab with you guys. And then we also want to acknowledge Chris Culp and Joanna Albala. They're the lab folks who have been really great at identifying speakers and inviting them over and bringing them over for our seminar series. So Chris Culp is the group leader in the Biosciences and Biotechnology Division at the lab, and Joanna Albala is the Education Outreach Manager for the Science and Technology Education Program. And then from the LPC side, we want to thank all the faculty who encourage their students to come. I see a lot of you here today. Thank you for coming as well. And also the classified professionals and administrators. Let's see, I don't see anyone here. But we want to thank them as well. Let's see here. Just a few more things. Our planning team consists of Kelsey Watt. Where is she? Big thank you to her. She does a lot of the work to get all of these from beginning to where we are now. So we should thank her. We also have David Lee to thank. He's been helping with our audiovisual here, getting all set up so that we have nice audiovisuals for you guys, for our speakers. Of course, thank you to the Dean's Office, Nano, and Linda Cross. They help a lot in putting this together as well. And then finally, our part of the big planning team, we have Robin Rehagen from physics right there. Woohoo! I think Mike, let's see here. Dr. Ansel is somewhere you know. He's part of the planning team as well, right? So you all know him, right? And then Keith Level from engineering, but also want to acknowledge Dr. Zing, Barbara Zing. She invited some student hosts for us today, right? So a lot of people to thank. And finally, just from the past, people who have been really helpful, Dr. Neil Eli and Dr. Lisa Everett. They were our former deans. And also from the lab, from the original team, we had Dr. Beth Vitalis and Dick Farnsworth. Right, so now, finally, on to our talk. This is Dr. Erik Mukerjee, and apparently you can call him Erik. And
nobody calls me, I'm all right. Nobody calls me Dr. Mukerjee.
Yeah. All right, so he's a member of the technical staff in the Engineering Directorate and Center for Micro and Nanotechnology at the lab, of course, Lawrence Livermore over there. And get this, okay, ready? He received his bachelor's in biological sciences, one. He received his master's in electrical and computer engineering, right? And then, guess what the PhD is on? Biomedical engineering, all from UC Davis, okay? So really, right, so a really good example of the interface between, science, biology in particular, and engineering. All right, so his research areas of interest are monitoring and manipulating human physiological systems through interfacing with biomems microdevices. I will let him tell you what biomems stands for. It's a long one. Okay, so lastly here, in addition to his technical work, he also serves as a member of the DoD, Department of Defense, I would say, yeah, Department of Defense Forensic Science and Technology Working Group, and has co-authored lots of papers and conferences on both engineering and biology. So his talk today is on microneedles. As you probably all know, he will focus on the application space of microfabricated needle systems for direct interaction with the epithelial, multi-layer, and dermis. So let's give him a round of applause.
Thank you very much. Okay, so I thought I was going to walk out here cold. I didn't realize I'm going to have such a wonderful introduction. So, oh, I can do this.
Getting things done in life requires the right tool.
Okay. I found that on the internet, and I just thought it was hilarious because the whole point of my talk here is just whatever you do, you need to find the right tool for the job. If it's microneedles, if it's apparently blow drying your hair with a leaf blower, yeah, who knows. So, I am Erik Mukerjee. Please call me Erik. I am a staff engineer, a biomedical engineer at Lawrence Livermore National Laboratory. I've had a great opportunity to work there for about 14 years now. And I had the opportunity to work on various different projects, right? So at Lawrence Livermore, I told a group here just earlier, is that I have this opportunity now at Lawrence Livermore that you can come in as a biomedical engineer. I'm a biomedical engineer. I work on biomems. I'll get to that in a second. And I have that opportunity, but for 4 years, I did none of that. I did nothing to do with biology. I worked on explosives. I worked on polymer science. I was a polymer scientist for a little while. And that opportunity gave me this breadth of knowledge. Now, with all that breadth of knowledge, we can go after some really weird and bizarre projects, right, at the lab, which fascinates me, and this is one of the things I absolutely love about the lab. So, tonight, you're going to hear me yammer. And I don't use that term lightly. Yammering is very important. Me, like most people at Lawrence Livermore National Laboratory, we're passionate about what we do. We love what we do. And if you ever made the mistake, about asking somebody at Lawrence Livermore, what do you do? I can almost guarantee you that you had this long-winded but enthusiastic rendition of their last project. This is what I bring to you tonight. The question has been asked already. What do you do? So tonight, I bring you my yammering. Okay, we're at the what if stage. What if you could take something that fills an entire room, normally, and put it in the palm of your hand? Well, from the 60s to now, we've done that. We've taken computers that filled this room, and then we put it onto your phone. So what if you could take that same technology and make a mechanical device that fits from a laboratory bench, something about that big, that can now fit in the palm of your hand or fit in a phone? We've done that. The gyroscope. The gyroscope is a great example of using technology to shrink something down, to take a mechanical entity and shrinking it down where it fits now into a phone or in a very small space. So what if we could make something so small that it is able to measure physical phenomenon that isn't possible on the larger scale? We've done that. Here we go. So this thing right here is a micro DSC. It's a DSC. It's a differential scanning calorimeter. Basically, it just looks at characteristics of material based on the heat. This goes at 20 C per second, right? This guy here is a MEMS version of it. I'll get to MEMS in a little bit, that we did at Lawrence Livermore. And that guy goes at 10,000 C per second. So this way now, we can look at phenomena that you absolutely cannot see with that one. So what if we can make smart devices that fit inside our body? So we've done that. We have pacemakers and insulin pumps and cochlear implants. So these are all examples of taking all that technology, cramming it down. Now you've made it biocompatible as well. So you've added that extra layer. So what if we could make these devices with precision, control, and reproducibility that isn't possible any other way? That is MEMS. That's micro electromechanical systems. So these are just a couple examples of what we can do in silicon. I'll talk about it just a little bit more. So what is MEMS, and why should we care? My favorite question to ask. One, it's cool. So if you see here, these are gears. This is an electrostatic comb drive that's used to probably move mirrors and things like this. And this is a dust mite. So that kind of gives you an idea of the scale of what we're able to do with MEMS. Over here on the right-hand side, This right here is a 250 electrode array that is implanted on the top side of your retina. It's an epiretinal prosthetic. So we developed it at Lawrence Livermore along with a consortium of other institutions. We made that. It is now sold in Europe called Argus 2, and it's embedded on top of your retina. What it does, it enables somebody who has macular degeneration that they cannot see anymore. It gives them certain contrast ideas where they can now see a screen that has a V or an I or something in contrast. They can scan it and they can actually see it in their head because these electrodes are now stimulating the neurons that are damaged. Okay, so quickly to the agenda. We're going to have two MEMS-based things. First, we're going to have silicon microdevice for transepithelial wound potential measurements, and then we're also going to have one for transepithelial fluid transport. And there'll be kind of two different sections to this. So I keep saying epithelial. So epithelium is part of the skin. So here's the skin. This right here, this kind of the top surface on here that's lighter colored, that's the epidermis. It's an epidermal multilayer, so there's 5 different layers in here. And then below that is the dermis. That's fibrous connective tissue. And it has blood vessels, capillaries, pain sensors, these kind of things. In the epidermis, you don't have capillaries, and you have very few pain receptors. That's going to come into play in a little bit. So this whole part of the talk is about wound potential. For when you're wounded, there's a field that's being set up. Now, how does that field set up? So what we have here is the skin is a battery. So from this top layer, the apical layer, or the top layer of this, all the way down to the basement layer, the bottom layer, we have a separation of charge. So sodium up here gets actively pumped into the cell and then diffuses into the interstitial space between the cells. And that happens over and over and over and over again. So what happens then is you have sort of less, you think about it, is less sodium up here and more sodium down at the basement membrane. It doesn't go into the dermis because of the basement membrane. What that does now is you have a negative effective negative charge at the top and a positive charge on the bottom. And that's because of the asymmetric pumping diffusion of the sodium. So what? Well, it turns out that in different stages of healing, the first thing that happens is that you have, it's back there. The first thing that happens is that you have this separation of charge I was talking about, right? So a little more negative here and a little more positive down here. And the reason why the sodium can't go back up because it's a high resistance pathway. You can't get the sodium can't easily go back up to that where that negative area would be, negative charge area would be. So in inflammatory response, you get a cut. You breach that, and you suddenly make this low resistance pathway. So all the sodium that's here says, woohoo, and up it goes. So now it has a low resistance pathway to be able to go up and sort of make the concentrations go to equilibrium in concentration. So now you have sodium that has been aggregating here, goes back up here, and then it's being laterally pumped out, and then it goes down. So you basically get these currents now that are happening on both sides. So now you have, in the center of this, you have sort of a positive, and then you can think of it as a little negative. And as you go further out, where it's out here, where it doesn't, the sodium doesn't sort of feel the attraction of this low resistance pathway, it's the same as it was before, kind of negative on top and positive on the bottom. The next stage is epithelialization. So keratinocytes migrate to the wound, and they are the first response to a wound healing, right? So they're the first things that go. The keratinocytes mediate every other cascade that happens. So they migrate to the wound. Then you get fibroplasia, so you get the fibrous connective tissue starts regenerating. You get neoangiogenesis, so you're making more capillaries, so there can be blood flow to that area. You get collagen rebuilding in the areas, and then finally you get the closure of the cell. Of the wound. So now you then set up this sort of negative on top, positive on the bottom. But during the time there was the wound, you had a difference in that. You didn't have negative on the top and positive on the bottom. You had it reversed. And if you go laterally out, then that becomes a field. So we're going to focus on the epithelialization, those keratinocytes that were sort of migrating here to the wound. Okay, so there has been evidence in the past that that there are fields in wounds, right? So the first one was an ionic current that was measured in 1791 on a forearm incision. In 1791, I did not want to be the person that was getting that incision. But since then, we've done a lot more experiments with cells in vitro. So here we have guinea pig. KV is a type of guinea pig skin, which is Barker. I'll talk about Barker a lot because he was the person that I followed when I did a lot of my research. We've done stuff in salamander skin and newt skin. And then the first human one where we could actually measure a current was an accidental amputee. So apparently somebody was on the short end of that knife. This was in 1980. And they measured current densities of 10 to 30 microamps coming out of the tip of somebody's finger. So we know now that there are these fields. So again, why does it matter? Well, it matters because some cells exhibit something called galvanotaxis. So galvano meaning current, taxis meaning moving. And so what happens, So what happens is that in the presence of an electrical field, it expresses certain proteins on this leading edge. This is just GFP. It's an indicator molecule. And it's expressed here while it's expressing this other protein. And what happens now is you have these proteins here. It puts out a process. It sticks down and it pulls it, kind of like a clam does. And that's how cells will move. So cells do experience movement, directional movement in electrical fields. So we've shown, many people have shown back in 1892, that there was aggregation of cells to an electrode, and then some other more eloquent studies happened later. And finally, keratinocytes shown by Nishimura, that they too show galvanic taxic response, which is excellent. Because if you remember, keratinocytes are the first cell that starts that cascade of wound healing. Something that's even, not better, but something that corroborates it too, is that Barker also showed pharmacologically, if you stop those sodium channels, right? Sorry, the sodium channels, the active sodium channels from pumping sodium so it goes down, 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 so you have that separation charge. If you stop that pharmacologically, it retards the rate of growth. So now we know we have fields in humans. We have fields. We know that cells now migrate in those fields. And we know that if we get rid of those fields, then healing kind of slows down. Excellent news. So why don't we just take a car battery and a couple of jumper cables and shove it onto a wound? One, it's not a good idea. Two, there's a little problem. So these are some studies that have shown that if you put the cathode, the positive end of a field, at the edge of the wound, that heals. Somebody else showed if you put the negative end of the field to the wound, that heals. Somebody has shown that if you do low pulsed current, direct current, if you do high voltages, if you do low current densities, and on and on and on. And the problem is that there's no consensus. So we have all this research, but it seems to be contradicting itself, which can be problematic. And the question is, why? And that's where we come in. That's what we wanted to do. So currently, if you look here, right, so this is the breached skin. So we have the normal negative on top, positive on the bottom. Think of this as way outside. So here's your cut, way over here, it's normal. So the sodium that's on the bottom here isn't affected by this breach. So it sets up this sort of normal negative impact. At the breach, you get an inverse of that. So Iserov showed that if you can put two electrodes just underneath the stratum corneum, which is this layer here, then you push it down, then you got a positive response. If you pushed it down further to the basement membrane, you got an inverse of that response, even more excellent. So that means we need to have some kind of depth control. We need to be able to control the depth of where these electrodes will go. Barker showed that if you laterally, so we're looking in this direction away from the wound, if you look laterally, the field itself dies out quickly. So what he's saying here is that as you go, looks like, away from the wound, the sodium concentrations becomes normal, as if it doesn't see that breach, as if nothing is wrong with that skin. So that's what it's telling you here. So we need to have precise control over the depth of our sensor, and we have to have precise control over the spacing, the lateral spacing from there. So the problem is that all these experiments you saw for the KV, so for the guinea pig, for the salamander, and for the newt, they're all sedated. It turns out people don't like to be sedated if they don't have to. So the way that they did this is typically with a drawn glass pipette. So that takes, I don't know if you guys are, a Pasteur pipette, right? It's pretty sharp, about the size of a pencil, and it comes down to a tip. Well, they take that, and they put it, and they do a little glass blowing with it, and they stretch it out to make it even thinner. So now it's unbelievably fragile. But it's very sharp, and it's very good for doing these experiments. The issue is that if somebody breathes, it breaks. If your heart beats, not joking, it breaks. So you can't do any of these studies in humans at all with a drawing glass pipette. Chloride silver wires, they're tougher, but there's issues with the silver salt. It's damaged, usually is damaged upon insertion, and it also happens to be a bit toxic for you. Vibrating probes are great. That's what was done on that amputated finger, but it's only on the surface, so that causes an issue as well. Implanted metal wires and hypodermic needles are fantastic, but they cause a lot of damage when they're placed into the skin. So over here, this is kind of a little micrograph, and I'll show this one again. Those little things floating around, those are blood cells in here. So we chose to go with a silicon microneedle. Right, tool for the job. Let's move here. So here's the device that we made. Here's a schematic of it. Here's the actual device. Over here is a dime. And you'll see in a lot of these sort of MEMS pictures, we always like to put in a dime or a penny or a quarter or something that gives kind of real world, something you can refer to, right? So a dime, I measured it in my office today, it's about 1 millimeter thick. This glass that it's on, this sort of glass here, this glass is a 0.5 millimeter thick. These guys are only 200 microns tall. So we have an array of 20 by 20 silicon microneedles. I'll show you a bigger picture in a second, on 300 micron center. So now we have precision on the depth we can go, and we have precision on the lateral spacing that we have. And again, this is all because of that MEMS. It's bonded to glass, which nicely electrically isolates them. So each individual needle is going to an individual trace, which is right here. So they terminate now onto these, we call them traces, but they're just basically electrical conduits to pads, and then those pads go out to a computer. And it makes an ohmic contact, which is very important. And then the tips are metallized, and the nice thing about them is that they only conduct at the tip, just the tip, not the shaft, but only the tip. And then lastly, we have a wound window, which we either use a lancet to make the wound, or we use a laser. I'll get into those two. Okay, so pretty pictures. So there's an actual picture of the array. It's a little bit closer, so now you can see that it's kind of on a pedestal, so these microneedles are on pedestals. And then again, they're all separated, so they're electrically isolated. This guy here, you can see that it looks like something is flaking off. That's silicon nitride. That's what we use to passivate the surface, so it doesn't conduct off the shaft. And then only at the tip does it conduct. So we know exactly how deep we're measuring. And finally, you can see just how sharp these are, and this is my little ghost in the machine, because it looks like a ghoul, so I put it up on every presentation I give. Even if it's not, it doesn't matter. Okay, so let's get to the experiments. So the first thing we did is do ex vivo experiments. So here's a piece of tissue. Here's our device right here. And you can see this kind of weird clamping device over it. It's connected to this connector that goes off, and then it goes to the computer. And it goes to some other things. What you see, I don't know if you can see it here, but there's a little slice in this one. It's because we have to physically take a lancet. A lancet, by the way, is basically it's a razor blade, pointed razor blade. A lancet to make the wound itself. And then we have our ground and reference over there. So this is not the easiest thing to see. But basically, we take measurements for about 10 minutes. And then we hit it with the lancet. Boom. So here's the lancet. And you can see that there's a precipitous drop in the voltage that's there. And then there's a period of recovery. So this happens only when we puncture the skin. If we just push something that's dull on the top of the skin, we don't get this response. That's the question I asked. And so if you take that and you just measure the magnitude of that change, you can see that this drops off with position. So this is voltage and this is position. Drops off somewhere around, 1.2 millimeters to 1.5 millimeters away from the wound. And so this is in human skin. So we're now showing that in human skin, we get the same type of data that we get from those guinea pigs. And now if we look at the field itself, we can see that it drops off as well, at this weird spurious point. But we can see that it drops off as well. So we have these really good trends that back up the data, or not back up, that is corroborated by the animal model data. So we fabricated the microneedle system. We verified the system. It matches with Barker's KV. Keep saying KV. KV is a guinea pig. Now it's time to move on to real-world experiments. So this is our in vivo system. That's my arm. And what we have here is you can see that there's the devices here. It's connected up through these connections to this box, which is a multiplexed amplifier and an ADD converter. That then goes to a computer. We have our reference ground electrodes on our arm. And nobody gets a pass. I got my mom hooked up to this system. We didn't get any data because the computer wasn't working, but I didn't tell her that. So unlike the other experiments the ex vivo experiments, and by the way, ex vivo, if you guys aren't familiar, I didn't say something earlier, but it just means that you've taken part of the body as a quantity and moved it out, right? So now that's what ex vivo. So this is in vivo. So now we're doing it sort of in the body, where it's normally supposed to be. So instead of using a lancet, which is a little tough to do, we are using a laser, this erbium YAG laser. So it's erbium and yttrium aluminum garnet laser, it's at this wavelength, which is really nice because that absorbs tremendously in water layers, which is phenomenal because when you're trying to make a wound, you want it to absorb and heat up and ablate what you're doing. So we have a short pulse width, and we can kind of hold it a little way away. What I didn't want to put on here, but I'm going to tell you anyway, don't tell anybody, is that where we are here is it's a dermatological skin resurfacing salon, which is why I'm using an erbium laser and not a CO2 laser. Because they didn't use CO2 lasers in that particular salon, and that's what I had access to, so that's what we used. But the erbium laser is a better laser than a CO2 because it absorbs 12 to 18 times more in layers that have water, and the surface of your skin has water. All cells have water. And so it's much better at ablating or heating up that material. There's less collateral damage, so your spot size is basically where you're going to make that hole, basically. So it takes less power and it makes it a little bit more safe. So look at that, data. So if it looks familiar to the ex vivo data, it's because it is. So now we can show, I forgot to mention, so now that we can show that we can have these trends not only in an ex vivo system, and I'm going to back up a second, that ex vivo system, right, that I used, we could see those trends, and it was fantastic. And remember I talked about that they pharmacologically stopped that field from happening? Well, in that ex vivo system, which we can't do in an in vivo system, is that we put tetrodotoxin, which is a sodium channel blocker on there, and that field disappeared. It just went away. So here we can't do it because my mom wouldn't like it, but here we can see that we have the same trends, which is just phenomenal. So that means that we now have this idea that the wound healing itself takes place because we have this field and because keratinocytes like to migrate to, and I would venture to say, the negative pole. So again, we can look at the field data, and it looks very similar to the ex vivo system. So in summary, for the wound potential, remember we have two parts, so don't get excited. We made the microneedles. We made it so it's electrically conductive only at the tip. It has a 1.2 mega ohm resistance. That's key because for biological systems, you can't have something that's not very resistive, because you'll get a lot of noise. So the higher you have it here, and this happens to be the sweet spot, that we got very good signal out of here. we had spatial precision, we have depth precision. And that's where the whole MEMS thing comes in. We were able now to spatially, radially put our needles right next to that wound, and we could measure every 300 microns for that wound. And we could measure exactly 180 microns down, which is what we wanted to do. We developed the interconnects and the supporting electronics and the lab view for doing the measurements. And most importantly, excuse me, we measured the endemic wound-induced, I have to read this one, wound-induced electrical fields in the epidermis, ex vivo and in vivo, that mimicked what we saw in the animal models. And so that makes it sort of this tantalizing step of maybe for somebody that has maybe a diabetic sore, which doesn't heal, and we could show that these wound potentials don't set up. Maybe the sodium channels, the active sodium channels aren't working as well. That's a possibility. What if we could put that field in? So no car batteries. This is a little bit more elegant. Okay, so for the second part, this is shorter. Oh, okay. Apparently I talk faster than I thought. So we're going to talk about a silicon micro device now that now can draw fluid up through the epithelium. So a transepithelial fluid uptake. So why? Why do we want to take biological fluids? Well, if you know, you get a blood test every whatever amount of time. It stinks because it hurts, and for some people, needles aren't their favorite things in the world. But the nice thing about blood is that it's a gold standard because it has biomarkers in it. What biomarkers are a myriad of different chemicals and biological agents and metabolites that are indicators of how your body's doing inside. So if, let's say you're diabetic, your glucose levels tend to go up or down, right? And so that's why they take a sample of blood to do the glucose. But there's many other ones. We can look at biomarkers for radiation detection. So if you've been exposed to too much radiation, your body reacts and it forms these globulins. So it's a prerequisite for monitoring. And like I said, blood contains these great biomarkers. But there's another fluid volume, the interstitial fluid, which is ISF. That's the fluid that bathes the cells, right? So in some areas of the body, blood isn't what's carrying nutrients to the cells. It's just sort of perfusing through. So after the capillaries, they come out of the capillaries, and this interstitial fluid perfuses through. It gives nutrients and oxygen to the cell and takes away the CO2 and waste, right? So it's a great system, but it's another fluid that has those biomarkers in it. And why is this important? Well, let's say you had to take daily volume, minute volumes for somebody who's a diabetic. I've used those Lancets. They are horrible. For some reason, they just hurt like the dickens. So what if you could do it in such a way that you could sort of do it continuously, or you could do it painlessly? That's what we kind of want to do. We want to look at. And so how can you get that fluid, the ISF or the blood, specifically the ISF? Well, we need the right tool for the job. Theme, right? So here is a 30-gauge needle. And just the tip of it, just that opening part, that's the hypodermic part, typically is about 3 millimeters. It might be 2, but it's about 3 millimeters long. The shaft on this one happens to be 2 inches, so that's 50,800 microns. I think in microns. And so what we would need to be able to access the fluid in the body is something that's 30 times smaller at the tip, 500 times smaller at the shaft. Why is that? It's because over here, this kind of pink area up here, I think it's pink, that's the epidermis, right? That you remember from the other one that was kind of the lighter one. Down here is the dermis, and this is the hypodermis, which has the fat and everything else. So this has capillaries in the dermis. This has no capillaries in the epidermis, has very few pain receptors, key, and then is filled with ISF. So there's ISF between all the cells. The question is, how can we get that with this guy, who's 3 millimeters long, when that layer is only 100, 150 microns deep? That's going to be a problem. So we need to fabricate something that has the ability, with sort of these abilities here, the ability to pierce the stratum corneum. So the stratum corneum is that top layer of skin. It's actually dead cells that are on the top. That's what we slough off, and there's dust all over. A lot of that is dead skin, I know. But it's very tough. That's one of the reasons why it works so well, is we are basically a bag of water. And it's keeping that water in us where it's supposed to be. So the stratum corneum is a tough thing to go through. We want to be able to extract fluid through that stratum corneum. We want to be able to have sort of a glucose detection system. So then we can sort of figure out whether or not we're getting what we think we're getting, which is very important. We want to have drug delivery capabilities. Turns out Krasnitz, if you guys have seen this, it's a really cool thing. He took a polymer microneedle that was impregnated with I think it's a flu vaccine. Wow. Flu vaccine. You press it into your skin, it dissolves. So there's no pain whatsoever. It dissolves, and then you have your flu vaccine, which is fantastic. And then it also minimizes damage and discomfort to the patients, because needles, most people don't like them. So again, we're going to use silicon, because silicon is a wonderful material to enable that precision and control on micron length scale. So we're going to take kind of the same approach we took with the wound potential, and now we're going to make it so it has a hole in the middle. So here's what we come up with. We got sort of 3 different designs. So the first one is volcano. Excuse me. First one is volcano. So we put the hole right in the middle because it seemed like a good idea, right? Put the hole right in the middle, have this beautiful shaft, we're going to make $1 million. No, it turns out that if you put the hole right in the middle, it becomes very fragile at the tip. And this guy right here becomes a skin plug. So you push it into the skin, it carves out this nice little piece of skin, and it just sits there. So you can't draw anything up. You can't actually push fluid out of it either. So then we thought, okay, aha, got it, hypodermic needle. So we offset it slightly. So we have, it's not a solid tip, but the tip is a little bit offset. It has more of a hypodermic kind of look to it. Great, not fragile. This thing can be repeatedly stuck into the skin. Awesome. And then it plugs up every single time, which is a problem. So I watched a lot of Discovery Channel. I was going to say as a kid, but I still do. So it dawned on me that I would see all these cobras specifically, so snake fangs. They typically have, except for the spitting cobra, they typically have a groove that goes down the back to inject when they envenomate their prey. And so that way, if they had a hole, it could be plugged up by the skin. If they have a groove, the skin's going to now be stretched around that groove, and the venom can go down, get into the little mousy mouse, and he's had it. So I thought, well, let's try it. So we offset the hole. So now we have a solid tip. We have a groove that runs down the majority of the shaft. And now when we pierce this into the skin stretches around it. The ISF goes into this area, down the shaft, goes to the backside, and then we can collect it. So here's what we made. Here's sort of the top side. So there's a piece of silicon with these microneedles etched into them. About 20 or 40 or so are connected to, and this is the backside now, are connected to holes that go all the way through, made up with these channels here. These channels go all the way back to a reservoir, and then through this, it's a glass plate on the back, and there's an access hole. So you can access whatever you're pulling up. Fantastic. So here's the beautiful part, right? I said I'd come back to this picture. This is a hypodermic needle, a 30 gauge, the smallest hypodermic needle I could find. That's the damage it does when pushed into the skin. So these are confocal micrographs. So you can look successfully in layers into the skin. It's kind of a cool trick without hurting yourself. And this is fluorescein dye. So these, again, are blood cells that are broken out from capillaries that have been damaged, and possibly other things. So here's, if you look down at the surface, so this is looking parallel, so I sort of went that way. If I just went straight down, this is the hole that it makes, the size of the hole. This is after it retracts, right? So you take the needle out, it retracts down. There's normalizing elastic forces in the skin, pulls that thing together. That's as much as it could pull together. On the same scale, that's a microneedle. That's how much that guy pulls together. There is much less damage, not to mention this kind of damage that won't happen with the microneedle. So, do you think we can deliver drugs for drug delivery? This is what we wanted, two-pronged approach. We wanted to be able to deliver drugs and take out fluid, hence the bidirectional fluid flow. So we used an Optiscan. This is the VA hospital in Sacramento. And what we did for the control is we basically just put fluorescein dye on your skin, left it there for a minute, and then wiped it away, and then used that confocal microscope, which is handheld, and then we successively took images down into the skin. So you can see that that fluorescein dye is only on the top of the skin. Again, the stratum corneum is a wonderful barrier, which is why we're alive. So now for the microneedle, we loaded up that microneedle channel with fluorescein dye, and we pressed that into the skin, then we applied pressure to the actuator. I had to put that on there. Basically, it's a piece of tape over that reservoir. You just press it. Very sophisticated. And then the microneedles were removed, and the skin was imaged. And again, so this one is just the control, and this one over here, B on the right-hand side, is the injection. So we're able to inject this fluid at a specific location to a specific depth. This is 180 microns down into the skin, which was the height of the needles. So we have demonstrated that we can inject fluid. Fantastic. But the holy grail of this whole thing was, can we extract fluid? So the procedure now is we take that snake fang device, we press it onto the ear. We ask people first. We put a clip on there just to have just a little bit of pressure, just to keep that pressure on there. Left it on for 30 minutes, we removed it, and we imaged it. So it turns out that we can. So if you have a microneedle that is 350 microns tall, is it deep, then it can go about 250 to 300 microns into the skin. Because of just the way the skin is, it's elastic. You can't really press the whole microneedle in there. But this is the backside channels I was talking about on that glass area. And you can see here, these are blood cells. These are red blood cells in blood. And if you do a hematocrit level here, so you count the red blood cells per volume, which is one of the standard things that we do when you take blood, this person was normal. Who knew? If you make them a little bit shorter, right, so this is going into where the capillaries are, where the dermis is, right, that I said that there was capillaries and some pain sensors, so it might hurt a little bit. If you make it 250 microns tall, you only go into the epidermis, which is fantastic because there's no pain sensors, there's no capillaries, and you get ISF. So you can see that there's blood cells here, there's no blood cells here, but it is fluid. And then we're thinking, what if somebody was really scared, started sweating, maybe we drew up sweat? Don't know. So we packed the back, that access hole in glass, with the chemistry from a glucose strip, a normal glucose strip for doing glucose measurements of the blood. You can see here that there's no red blood cells. So we packed that up, and then we put it on the earlobe, the 250 micron tall microneedles, it drew up the ISF, and lo and behold, we got a color change. Turns out that color change also was exactly the same as the color change when we drew some blood from the same individual and tested it on the same strip. Oh, it was already up there. So it's very important to know that we can indeed go after those two very distinct volumes, fluid volumes in the system. We can go after blood, and we can go go after ISF. And again, ISF is key because we can do this continuously, there's no pain, and you can basically leave this thing on for a period of time. I wore it for 4 days. Okay, so in summary, we did the wound potential measurements. Again, the keratinocytes have galvanotaxic response in a field. So we wanted to measure that, so we were able to make the device to be able to measure those fields in vitro and ex vivo. We made a bidirectional fluid transport device, so we designed and fabricated this thing. We had 3 different devices, the volcano, the hypodermic, and the snake fang. And we were able to demonstrate that we can inject fluid at a specific depth, and then we could draw fluid up. Those 2 fluid volumes, the interstitial fluid and the blood. So this is the end of my talk, but I went by the spire every day, and it kept taunting me to make a better needle, because it was hard to make these needles in the beginning. So I wish it would be quiet now. So the take-home message here is that no matter what you're doing, whether it is, you're brushing your teeth, you're driving in a nail, you're getting a haircut, you're blow-drying your hair, you're extracting fluid from the epidermis to look for biomarkers. or you're looking at the endemic fields and wound-induced fields in the body, the most important thing is that you have to make sure that you look for and choose the right tool for the job. Thank you. I was a little faster than I thought, so lots of questions.
Right. Do we have any questions? I'm sure we do. Who's on first? I see a hand here. Excuse me here.
So, how were the microneedles manufactured?
So the microneedles were manufactured. I don't know you. This is perfect. So for the devices, we started out with silicon. I'll just go through this quickly. It was started with silicon, and we used something called photo patterning. So this is what makes this MEMS technology so powerful, is that you take a photosensitive resin, a polymer, we call it photoresist because it's resistant to things. We put that onto a wafer. We spin it on really fast. So it's very thin, so it's about 2 microns tall. Then we put a glass, what we call a mask, on top of that. It has chrome everywhere. We don't want UV light to hit it. And that's patterned based on what sort of these features to be. We put that on top. We shine UV light on it. We take that mask off. We put it in developer, which is just a base. And those portions that were hit by the UV light, they go away. So now you have, again, 2 micron precision on a 2D scale of a pattern that you want. We take that, we take that, and then we can do things to it, right? So now we have this really precise photoresist on there. Now we can etch a little bit. Maybe we etch a little more. Maybe we grow something up in that area. So we have a lot of different ways that we can manipulate this. I'll just go to the next one. Maybe it's more interesting. Okay, so this is the Holland microneedle one. So we start out with silicon. We do this photoresist, and we pattern aluminum on here and then big photoresist on here. Based on that pattern, we stick it in something that's called a deep reactive ion etcher. What that does is it selectively etches in a single direction, more or less, in silicon, so we can make these long holes here. And then we can do some fancy stuff to make the channels I was talking about when the fluid flows on the backside. We flip this guy over, and so so that was that same sort of L shape that's up here, and now we connect it from a similar hole on the front side that's a little bit smaller. So now we have a hole that goes all the way through. We take that and anotically bond it to glass. So anodic bonding is just bonding of it. How much you want to get into this? It's bonding with, the glass has sodium in it, and you put it in a huge electrical field and you heat that thing up. And the sodium moves away from the surface. It creates what's called the space charge region, and you actually get chemical bonding right there. It's very dangerous because it's like 400 volts or 1,200 volts and a car battery, but it works really well. So we've now taken this, we put it on there, and then we etch this back. Sorry, we cut this back with a saw. Yeah, we have saws that are small enough to cut 200 microns, 100 microns. And then we use what's called, excuse me, HNA, which is hydrofluoric, nitric, and acetic acid together, which is really good at etching silicon, which is why we use silicon. And then we etch them into nice, sharp microneedles. So now we have this wonderful microneedle snake fang that goes all the way through to the backside. It goes to a channel, and then strew that out into the third dimension. Then it goes to that reservoir where you can access that fluid. Answer your question?
All right. Any more? Okay, all the way down here. Hold on. Yeah. Come down here a little bit.
Hi there.
Hi.
I just had a question about like the instrumentation you were using to measure the skin potentials during the incision. It seems like a lot of what you're doing works with like the specific chemistry of the skin, whereas I know a lot of like instrumentation amplifiers are speccing these things out in like amps. So I was wondering, like, are you guys spinning your own like silicon to like capture those kind of impulses, or is that like a an off-the-shelf kind of amplifier?
So I had the wonderful opportunity to have the best electrical engineer work with me on this. If you were to give me a schematic of the electronics in here, and yes, I am an electrical engineer, schematics, it would be Greek and I would have no idea. But this guy knew exactly, so if I told him the range that we needed to be able to measure, right, so we're obviously not doing amps, we're doing microamps or nanoamps. He specifically designed electronics that are theoretically off the shelf, right? He didn't do an IC circuit, an integrated circuit board. He did individual components. So it's technically off the shelf, but it's custom made off the shelf. And so that's the reason why we could get that kind of data, is because we knew what that range would be, and we customized our electronics to do that.
So you said that they can use this for drug deliveries, and if you were to put it in place, what about the chances of infection? How would you guys deal with that?
So that's a very good question, because we have a NASA project. Oh, NASA was another one. Somebody asked me about where funding comes from. NASA. We did stuff with NASA. And the biggest issue is making sure that it's sterile. So if we can keep this thing sterile, right, before it's implanted, clean off the skin just like you would in a normal blood draw, then you can keep the entire thing sterile. And so you would sort of avoid infection. The issue is that silicon, as you might know, isn't normal to your body, right? So not only do we have to worry about infection, but we also have to worry about foreign body response. So you put something in your skin like a splinter, right? You put a splinter in your body, it freaks out, it gets red because that's inflammation, it doesn't like it. That's your body trying to make sure that there's no infection in there. Then they don't encapsulate it, which is great because now if there is any bad things in there, it encapsulates the whole thing. And then it starts pushing it up and out, depending on where it is in your skin, but it can push it in. So that's why a splinter kind of comes out after a while, right? You get that horrible redness and all that good stuff. For silicon, we get a foreign body response, but we don't get a toxic response. So when you push this into your skin, it doesn't inflame. You might engulf it a little bit, but it doesn't inflame. So we don't have all these leukocytes, the white blood cells, coming in, rushing in, and gooping this thing up. So for us, if we can keep it sterile, then we're, from the get-go, with all the whatever we're going to inject into there, then we're golden at that point. If that answers your question. Basically, keep it sterile, and then it'll be sterile, and you don't have to worry so much about infection. It's the same issues that any biomedical device is going to run into.
Questions? Raise your hand if you're ready. We have another question from the same gentleman here.
So did you, in your experiments when you were measuring the electrical charge due to wounding, did you vary the depth at all? And if so, did it have an effect on the strength of the response?
So we didn't vary the depth. Because so something I didn't mention is that the epidermis, it's variable, right? So, for instance, my mom, she's older. So people that are older, their epidermis is thinner. So it gets thinner as you age. Depending on where it is on your body, your epidermis can go anywhere from the pads of your feet, I believe are 1 millimeter, all the way down to 100 microns or so, which is where we targeted sort of on the part of your arm. So unfortunately, because of that variation, it made it very difficult to be able to move it up or down. The reason why I said we have incredible precision on the depth is because we make the microneedles to go to a certain depth. Changing that without pressing it all the way in means there's going to be extreme variation on the depth of those. It's a very good question, but no, it's not something.
Any more? Okay. First, and then I'll go over to you, Joe.
So you said you manufactured the needles to be really precise in how long they are, but how do you know that they're all going down to the same depth? Because if it's like a flat panel, and then you have like no part on the body is really perfectly flat, so then maybe like the ones on the edges wouldn't go as deep as the one in the center, and like how did you factor that in?
You are absolutely right. Really observant. So, I don't know if I can get back here. Let's see. Oh, here we go. So, holy moly. Okay, so, right, if you noticed, I said that there was 12 guys that were electrically conductive. Those are 6 there, 6 there. There are 400 needles here. We originally made it so they were 12 needles. Everything broke. It just, So if you think about the amount of force it takes to push it into skin, if you pushed it straight down, awesome. That's what we call compressive force on those needles, and silicon is as strong as steel, right? So you can push on it up and down, and it won't break. Awesome. You give it any kind of lateral movement, snap. So that's where the problem comes in. So we made it, so there's 400 microneedles. What that does is exactly what you were talking about. On the edges, absolutely, it's not going in as far. But what it is doing is stretching the skin flat. And the microneedles that have the electrical connection are now going into a flat surface. So that's how we ensured that we were going down to the same depths. That is a great question.
So you measured the electrical potential difference when there's a cut or something, right? I was wondering if there's any such thing for other injuries, like burns.
So we didn't look into burns. We specifically looked at things that, let me back up. We didn't look at burns. We looked at cuts because they were easier to make. People don't like to get burned. Probably don't like to get shot with a laser, but they really don't like to get burned. But it's because of the mechanism, right? So if we get that low resistance pathway, suddenly we're going to set up that field. That's where the keratinocytes go. With a burn, it's generally a similar animal, but it's not exactly the same. Because with a burn, you still have a lot of material there. But if you breach the basement membrane there, so the blood now comes up, then you effectively set up the same thing. So there's a possibility this could also be used for accelerated burn. I don't know why I'm pointing here. The accelerated healing for burns as well. But we didn't look into that.
So when they take out blood at a hospital, the laboratory, they usually use EDTA for preventing clotting and all that. So when you're extracting blood in these, how do you prevent the blood from clotting into
So, very good question. So we heparinize the surface. So EDTA and heparin are two anticoagulants. The nice thing about silicon, big proponent of silicon, is that it's got these the silicon groups and oxygen groups is part of the matrix of it. The beautiful thing is that you can take and covalently make covalent bonds with other reagents on the surface. So I can now coat the surface of all the channels and everything with heparin. So I can heparinize the surface by doing a silanization, as it's called. So that's the way that we get away from the clogging. It's a good question.
Questions? Oh. No question. Raise your hand real high.
I was just interested in how you made this proposal in order to obtain funding for this project.
So this was a DARPA. So I said to a small group, now I got to figure out if I remember this. So DARPA is a defense organization. It's high risk, high reward. So you get sort of large sums of money for really wacky ideas. Defense, Advanced Research Program, Agency. Yeah, there we go. And so this was a DARPA project. The idea is that, for our idea, the idea is that we would look for heat shock proteins. So these are proteins that are in your system when you go into shock or you've been affected by something and your body is starting to react. So we would draw the stuff up, and then using something called EDP, we could separate out these cells and then look for those specific biomarkers. Back to biomarkers. But it's a specific biomarker we were looking at. So this was a DARPA project, and we got a lot of funding for this, and they worked out pretty nicely for us. And it was fun. Oh my God, it was fun.
Questions over here? No? Oh.
Did I hear you say in the beginning you coated the outside with silicon nitride?
Yes.
Because the rest of it looked like it said silica. It was.
So we only did, so basically we did the whole thing. Let's see, oh, it's up here. So basically we capped this off with a very sophisticated piece of tape. And then all these guys are just open. And so we just put silicon nitride everywhere. Excuse me. And so if you remember that SEM, that scanning electron micrograph, you could see the middle where there was something kind of fluffing up. Well, that was a silicon nitride that isn't sticking to the glass very well. So it's everywhere. And then what we did, so we have two methods of doing this. So we removed the silicon nitride from the tip by either ablating it, so we'd use a very high voltage on the end of a wand that I was allowed to hold, which I guess nobody liked me, so they thought I would hit myself. But we attached the ground to here, and then I had basically a 1200 volt wand that I would get close to the tip, and it would arc. I could see it arc, and I would just go down the line and arc everybody. And then it would take off about the first 3 microns of it, so we got really precise. Then we started going to just piercing it through aluminum foil, putting it in a reactive ion etcher, and removing the silicon nitride.
I see any hands. Oh. So maybe as a last question for our students, so your career path.
My career path.
And also how you partner with different types of people at the lab.
Okay. Career path, torturous path. Let's talk to some people here. So I'm a undergrad from UC Davis. I'm a biological science major. I wanted to be a physician. Then I decided to make a turn, and I started getting interested in engineering because a friend of my family actually, had me start making these DNA platforms. We're trying to make 1,000 DNA channels in agarose gel on something about that big. It never really happened, but it got me interested in engineering. Because before, engineering was this weird thing that only, pocket protectors and the whole bit, right? So I didn't understand that at first. He got me interested, and from there, I got my master's in electrical engineering, which was quite a departure. It took some time. It took a long time. Because as a biologist, we take certain classes. As an engineer, you have to take the same classes, different level. So I had to take all those other classes. So I took 11 classes to apply to the program. I don't suggest it. Now it's great, but I don't suggest it. Then from there, I decided to meld the two and went and got my PhD in biomedical engineering. So I'm a biomedical engineer. So I took that biology, it wasn't a waste, and I took the engineering and I stuck them together. So my career path was, once I graduated there, I went to Lawrence Livermore as a postdoc. And as a postdoc, you have to have funding. So somebody was there, I went and interviewed, and they said, great, you can come here and you're going to work with this one person. Excellent. She works in the medical technology program. I do medical technology. That's fantastic. A month before I got there, she left with the money. So I got to Lawrence Livermore with no job, right? So for 4 months, I wandered around, and I just sort of talked to people. Anybody that would leave their door open accidentally, I had this little portfolio, and I go, hi, my name's Erik. It actually got me to go all the way up to, so our levels are, we have the director, and then we have the principal associate directors, and we have the associate directors. I went all the way to the associate directors because I didn't know any better. So apparently I was talking to the associate director saying, hey, my name's Erik Mukerjee. But the nice thing is that they remembered me, right? And so it made an impression. And so from there, I was a 1-year postdoc, and then I became a staff scientist, and I've been a staff scientist ever since. And it has been awesome, in case I didn't mention that. Yeah, so as a biomedical engineer that does MEMS and biology, I spent 4 years doing none of that. And that is the beautiful thing about the lab, is that we collaborate with everybody at the lab. So on the NASA project I mentioned, right? So I do sort of MEMS, the biomedical engineering portion. We have an optical physicist that works with us to do some photo detection. We have 3 biologists that work with us to do the biodetection on this particular platform. So that's not great. That's only 3 different disciplines. But I've worked on other projects where we have, I've got to remember this, we have an engineer, we have a chemical engineer, wherever she went, chemical engineer, there you go. Still don't know what they do, but chemical engineer, we had a physicist, we had an electronics engineer, we had a biologist, that's 5, and there's more and I can't remember it. So we work with a whole bunch of different people, and even in just my building that I work in, I can walk down the hall and I can find almost any kind of engineering I need, plus some physicists and some biologists too. You can walk across the street, and in our microfabrication area, it houses BSL-2, so it's a biosafety level 2 research facility. So we can use human cells. We can actually do attenuated AIDS research in there if we want to. So we can do HIV research. But it's fantastic because you have all this capability all in this little 1 mile area. And it's fantastic. If you have a crazy idea, one last thing. So I had a crazy idea about doing biomarkers and doing some other things. I don't know that much about biomarkers, but I need to learn about biomarkers. Turns out that we have this place called the Forensic Science Center, which is fantastic. And I think Brad Hart came in and talked to you. So he's the center director, and I went to him and I went to some of the people there to get a better idea of how you detect these things, what they might be, and what are the detection limits. And so I had this crazy idea that I had no idea if it would work. I got to go talk to somebody who's a chemist and then a biologist, and suddenly it comes to fruition, and we get money, and then we get to do this biomarker research. It's phenomenal that it's just all there. Almost any kind of discipline is there, and we basically work with them all, especially as an engineer. I should mention that. As an engineer, we work with everybody. The biologists work with a lot of people. The physicists, they stay in their own. We won't talk about the physicists.
What a wonderful talk. Thank you, Dr. Erik, I should say. Big round of applause.
Thank you.
All right. Well, hold on. Thank you. And one quick announcement. Our next seminar is November 1st. Dr. Graham Bench will come and talk about accelerator mass spectrometry, peeking at particles of human health.